Hey class, this is Mr. Robert, Shasta High School. We're looking at what could be the last official study team test of the year. We may have another study team test for Chapter 11, but not entirely sure. We are in Chapter 11 now, and let's go ahead and look at this. There were 4 pages, front and back side, Part A, B, C, and D, and they're all done. But let's go ahead and look at the solutions. Maybe some of you can check out things you did, fine tune them. Again, if this is not helpful, please do not sit and watch this. There's nothing magical about pushing play on this video and then going out, to watch TV in the living room with the rest of the family. So if you're here and you're going to pay attention, good luck. I hope you find it helpful. But if you got better things to do and you don't really need to, review this stuff, please don't do me a favors. Well, whatever. First question says, these are the annual numbers of deaths from tornadoes in the United States from 1990 through the year 2000. So if you include both of those endpoints, the 1990 and the 2000, there are 11 years there, and there's 11 data values there. And it's asking me to do basically just kind of hunt down a bunch of statistics, lowercase statistics, like, for example, the mean, which is a measure of central tendency, the median, measure of central tendency, and then the standard deviation, the interquartile range, both help me describe the spread of the distribution, and then the 5-number summary there. So I'm going to go ahead and bring the calculator over and enter these values. So to enter data, again, on our calculator, we press statistics, and then go to edit, and you can see, oh, they're already entered. That's nice. You don't have to watch me do that. So I do have to start with the 53 and then go to 39, 39, 33, then 69, 30, 25. I'm just checking them. 67, 130, and 94, and then 40. And yeah, 11 values. Very nice. Now, if I want to do the one variable statistic analysis with these, right, I'm just going to press second stat. Nope, not second stat. Just, oh, I don't want that. There we go. Stats by itself. Calculate, and then the first option there is one variable statistics. And I'm reading things from list one. That's where my data is. That's convenient. Press enter, 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 and here we go. First value off the top there is the mean, and you can see the mean of my data, if I round to the nearest tenth, is 56.3. So let's go and write that down. This was 56.3. The next value is standard deviation, and that's this thing right here, the lower Greek letter sigma of x, and you can see for this problem the standard deviation is 30.5. We've got 30.5. The range of the data is the difference between the maximum value in our data set and the minimum. And if I hit the down arrow here a few times, I can go down to where my 5-number summary is, and you can see I can see both the max and the min. So the max is 130, the min's 25, so 130 minus 25 gives me the difference of 105. So the range of this data is 105, which is nothing. Let me rewrite that with that turned off. 105, which is nothing more than 130 minus 25. Outliers, when I look at this data set, I would say potentially the number 130 is an outlier, maybe even 94. In Math 3, we're not being very particular about how we identify outliers. When we get into AP statistics, there'll be more information to come about how we determine whether or not a number is really an outlier or not. Let's go down to mode. The mode of this data set's 39, right? The number 39 occurs twice in the data. Interquartile range is the difference between Q3 and Q1. And I can see on my calculator Q3 is at 69, Q1 is at 33, and 69 minus 33 is the number, it's 36, yeah. So my interquartile range is 36. And then down to my 5-number summary. Again, this is a perfect place to be on my calculator screen because I can see the minimum is 25. Q1 is at 33. The median is at 40. The Q3 is at 69, and the maximum value is 130. So there it is, some some one variable statistics. A couple things that we notice if we want to talk about, you know, the center of our data, right? We have two things. We can use the mean and we can use the median to describe the center of our distribution. Um, if our distribution is skewed left or right, it pulls the mean and the median apart from each other. And in a distribution that's fairly skewed or it has outliers, we do not want to use the mean and standard deviation to describe the center and how spread out the data is. We want to use the median in the interquartile range. So I guess I'll highlight that. In the case of a distribution that is skewed left or skewed right, um, probably the thing that we're going to be looking at is the median and the interquartile range to describe the data. Um, they tend to be a little bit resistant to some skewing. If our data is symmetrical, best tool we have for describing how spread out the data is our standard deviation. And in the case of a symmetric data set that's not skewed, the mean would be probably the way to go with for describing measures of central tendency. All right, let's go on to question number 2. Question 2 says, sketch the solution to each system of inequalities. So when I look at these things, right, the thing is these are both boundary conditions. I've got two boundary conditions for this problem. And I can see that in the case of the first one, my y's are greater than the boundary. Now, this expression that defines my boundary, actually, it's the equation y equals negative 5 halves x minus 3. Right? That has a y-intercept at negative 3. I'll put a dot there. And it has this slope pattern of down 5 over 2. I can also go up 1, 2, 3, 4, 5 units, and then go backwards 2. So those 2 points are defining my boundary. Let me grab the ruler, and I'll just line this up here. So because this boundary condition says y's are greater than that, it's not a solid boundary, right? This is a dashed boundary line. See, I'm drawing a dashed line. And if I was to test a value, right, my value that I would test would be 0, 0. So that means that x is 0 for that point, and y is 0 for that point. And if I plug that into this inequality, it becomes, on the left-hand side, 0 is greater than, and in the case of this is also 0. So it's 0 is greater than 3. No, negative 3. That's right. That's the negative. 0 is greater than negative 3, which is true. So because this is true, right, I have confirmation that the y's that I want are the y's that are above this curve, right? So I'm looking at things above this particular line. Not on the line, but strictly above it. And I can see that from the inequality as well. The other one there is y's are less than or equal to, and because this is the boundary it's less than or equal to, this will be a solid boundary. My slope is going to be down 1 unit and then over 2, negative 1/2, and I've got a y-intercept at 1. So I can graph that straightforwardly. I'll put a dot here at 1, and I'm just going to go down 1 over 2, down 1 over 2. There we go. Again, because this was less than or equal to, being very careful here to select draw a solid boundary, because it's not only the points above or below that, but also on this line that works. So which one is it, above or below? Well, you can see it says y's are less than that line. So because my y's are less than or equal to, I'm pretty sure it's below. But just to help make myself feel super happy, again, I'm going to test 0, 0. In the case that when y is 0, I get a 0 on the left-hand side, and that is less than or equal to. In the case of x is 0, this just becomes 1. That's a true statement, right? 0 is less than 1. So because that's true, I know that I'm shading below the green line. So my solution looks like all of these points that live, roughly in between these two. So, right? Any point that's in this region that I've kind of marked off, those xy pairs would satisfy both of those inequalities. It would make both of them true. And that's what a solution is, right? It's a xy pair that makes not just one, but both of the inequalities true. And because it's an inequality, it's not just the single point, perhaps, where the lines meet, but it's many points. All right, let's go over to the next problem here. I don't know why this says this is number 3. This is just part B of question 2. Let me get rid of that. So let's look at this. So the first inequality says y's are greater than 3. So I've just lined up my ruler here for y is equal to 3. And we don't have y is equal to 3. It says y's are strictly greater than 3. But I do want to point out that all the points that are on this dashed line, right? Well, it would be the solid line if I was talking about all of them. All the points on that, y values are exactly 3. And I need y's to be more than the 3. So I'm shading clearly above these lines. So y is greater than 3 is the first. The other one has an inequality that is not in slope-intercept form. So I'm going to kind of carefully attempt to get this into a changed form. So I'm going to rewrite it first of all. I'll just write it 2x minus y is less than 3. I'm going to take 2x from each side. If I take a 2x from the left-hand side, it just becomes a negative y. On the other side, when I take away the 2x, I'm going to insert it here. They've got negative 2x and then plus a 3. Now, I'm going to multiply both sides of this inequality by negative 1. And it's not magic why this happens, right? You can always consider, look, this is clearly true. 5 is less than 10. If I multiply both sides of this by negative 1, it becomes negative 5, and I get a negative 10. And which one is larger now? Well, it's switched directions, right? This is the larger value now. So when I multiply both sides by a negative value, in that case negative 1, or if I were to divide, that's just multiplying by a reciprocal. Multiplication and division by a negative value causes the direction of the inequality to switch. That's just a justification for what I'm going to write down here now as I carefully multiply both sides by negative 1. I'm going to get a positive y, and now it is greater than a positive 2x and then a negative 3. So I can see my slope is positive 2 up 2 over 1, and my y-intercept is at negative 3. So I'm going to go down to negative 3. I'll place a dot there. Then I'm going to go up 2 units over 1, up 2 units over 1. That's enough. I can grab my ruler, line the ruler up. Whoops. And then from there, it was greater than, so it's just a dashed line. So I'll just go ahead and dash these lines. And there we go. And again, y's were above this curve, so I'm looking for things above that. Now, the place where I'm both above the green dashed line and above the red dashed line is this area right here, and I'll just kind of shade it in blue. So all these points, and of course this extends forever off to the left, and it keeps going up forever. But any xy points in there would work in both of the inequalities, and they would points in other spots might work in one, but not both. And then there's one region where none of the points would work for either, or the points would work for neither. But I digress. Let's go on to question number 3, the actual number 3, solving some absolute value equations, not inequalities, just absolute value equations. It's very similar to absolute value inequalities. But let's take a look at the first problem here. I'm going to, again, to deal with the absolute value, the thing we need to do is isolate it first. So if I want to isolate this absolute value of x, I'm going to divide both sides of this by negative 3. So when I do that, this is going to become the absolute value of x is equal to negative 15 divided by negative 3. You can see both sides are being divided by negative 3. Well, negative 15 divided by negative 3 is just positive 5. So the absolute value of x is 5. There are two things that this can be, right? This x can be. Either it is the case that x is 5, right? In which case this solution works, right? I mean, if that works as a solution is absolute value equation because the absolute value of 5 is 5. Or it could be the case that x is negative 5. And if negative 5 was substituted into that equation, I would get the absolute value of negative 5, which is indeed equal to 5. So you can see both of those work. And that is a very nice, simple illustration of how we deal with these absolute value equations, right? We have to break it up into two separate equations to consider what's going on. Let's move on to Part B. Part B does have the absolute value portion of the inequality completely isolated. So let's go back to this thinking. This thing that I'm highlighting, the values inside of the absolute value, right? That x minus 3.2, the thing inside, is either negative 5.5, right? And that would be great because if that was the thing I highlighted in green, if that was negative 5.5, the absolute value of it would be 5.5, and this would be a solution. Or the other way to think about this is that thing inside the absolute value, the x minus 3.2, would be positive 5.5. So those are the two equations I get, and this is the trade-off. When I want to get rid of that absolute value notation, right, I have to think about two different things. The absolute value is kind of nice because it allows me to collapse it to just that one thing, but now I've got to think about the two things. So in the first case, and well, in both cases, actually, we're just going to add 3.2 to both sides. If I do that here, I get that x is equal to, so I'm adding 3.2. This becomes negative 2.3. So that's one of my solutions. Or the other solution, again, adding 3.2. This time I'm going to get x is equal to, is it 8.7? Yeah, positive 8.7. So there are two values, right, that x can be. X is either negative 2.3 or x is positive 8.7. And if I go back over here, by the way, it's important to put that. I should put that or, because clearly x cannot be 5 and negative 5 at the same time both, right? It is either 5 or it's negative 5. Let's go on to C. Fairly straightforward, right? This thing inside the absolute value, the 6 plus 2x, is either going to be 6 plus 2x is either going to be negative 12, right? Or the 6 plus 2x is going to be positive 12. For each of these, I'm going to take away 6 first, so this gives me that 2x is equal to negative 18. And over here, I'm going to get that 2x is equal to, taking away 6 from both sides, positive 6. And then I divide by 2, so x is negative 9, or x is the number 3. So those are the two solutions for that. Negative 9 or 3 are both valid substitutions for the original inequality. And then finally, D, right? The first thing I need to do here is make sure I get the absolute value isolated. So I'm going to add 5 to each side of this equation. And I get the absolute value of 2x is equal to the number 12. Okay, so that means, again, following the same pattern, same thinking, either 2x is equal to negative 12 or 2x equals positive 12. Therefore, dividing both by 2, x is negative 6, or dividing by 2 again, x is positive 6. So those are absolute value equations. We've also, of course, looked at absolute value inequalities, and that's on another portion of this. Let's move on to the back page of Part A here. It says a small toy company makes only cars and trucks. The profit made on cars is $2, and the profit made on trucks is $3 each. To stay in business, the company must make at least $500 profit each week. The company only has the resources to make up to 200 total cars and trucks each week. Okay, so first of all, write a system of inequalities that represents possible combinations of toys that the company can make and the amount of profit they will earn. Define your variables. That's a very important statement, right? It's important that we know precisely what we mean by our variables. And I'm going to go ahead and say I'll write let. That's a nice way to say to the reader that I'm defining a variable here. I'm going to set let t be the number of trucks produced. See, it's not the profit from the trucks. It's not what a truck costs. It's just how many of those I'm making. And I'm also going to say let C, and I'll just do these, be the number of cars produced every single week. Now, there's two constraints. The number of trucks that I produce plus the number of cars that I can produce can be no more than 200, right? I can make up to 200. Right? I can make it I can make 200 but not more than 200. So 200 or less. And that's one of the constraints that I can read. It says that they have the resources to make up to 200 total cars and trucks each week. So that's one. The other restraint that we have here is that our profit has to be it has to be at least $500, right? 500 or more dollars. So let's think about profit. Every single one of these trucks produces $3 of profit. So I could say 3 times T. That's the amount of profit I'm getting per truck plus 2 times C. Okay, so this expression that I've written is the profit from the number of trucks, because every single truck is producing $3 profit, plus the profit from every car, because every car is producing $2 profit. The profit I'm making has to be at least $500. So $500 or more than $500. Okay, so those are the two constraints that I have. Now, the last question is, can the company stay in business? If so, how? And there's a lot of answers there. And some of you did, I appreciate it. You got some graph paper and you assigned, I think T to X and C to Y, and you were looking at this and trying to find the region. But if you just try a couple simple values, and I think some of you did, look, if I did 100 each, right, 100 trucks and 100 cars, if I had 100 trucks, this would produce $300, and 100 cars would produce $200 in profit. So together, right, they are making $500. So exactly 500. Then I could ask the question, well, what if I wanted to maximize the profit, right? I wanted to make the most profit. And some of you were saying, well, if I had exactly 200 trucks, right? So, and you could do this. You could say trucks and cars. And you could write down a couple solutions, right? If I did 100 trucks and 100 cars, that gave me $100 profit. But I could also do, for example, all 200 of my cars or my vehicles produced would be trucks. That would give me $600 profit, and I would be making 0 of the cars. So there's a lot of different numbers in there that work, but the important thing is I can't exceed my production limitation of only 200 toy vehicles per week, and I also have to make sure that I'm getting $500 or more for the profit. So, okay, let's move on to question number 5. It says, given the linear function f of x equals 5x plus 3, find the new expression for each below, and then it says describe the transformation. So what's happening here is I've got this function, right? And the function was negative 5x plus the number 3. And what's happening, of course, with this is true of any function, right? If I give this function, for example, an input value like the number 2, right? When 2 goes into that function, I get 2 times negative 5, which is negative 10, and negative 10 plus 3 gives me the value 7. So right here is where y is 7. So a value of 2 goes in, and a value of negative or 7 comes out of it. Now, if I was to take this function and it said subtract 10 away from everything, well, if I was to subtract 10 away from this negative 7, it wouldn't be giving me that anymore. I'd be decreasing that output by 10 units, and it would go all the way down to negative 17, right? So now this would be the new output in that case. So let's go back and look at this. We're looking at this function such that every single time I produce an output from my function, again, an x value goes into that, and when I evaluate it, this f of x represents the output that I get as I place x values in it. Well, this says I'm going to decrease the output by 10 units. Well, all of a sudden now, if I'm decreasing the output by 10 units, I'm taking this curve and I'm shifting the entire thing down by 10 units. So that's the description of the transformation, right? Shift all outputs down by 10 units. And then it says write an expression, right, for what this looks like now. So you can see the expression is the part of this. This is the part of the function, right? This is the function name. This is what the function's taking it as an argument. And then it produces the output according to what this expression says. Well, this new expression would now be negative 5x, and I'm taking away 10. So this would now be minus the number 7. 5x minus 7 is the new expression. So there's my description, right, and the new expression. So both of those parts are required as answers. If I look at 6, you can see this is a little different now. Again, the f of x represents the output after I put in a particular value of x. And this now says every single time you produce an output, you're going to increase by 5. So if I'm looking at this, whoops, I can't see that. Never mind. Sorry. You increase by 5. So this is now shifting. Oops. I didn't want to write f of x. Shift all outputs up 5 units. Right? Everything gets increased by 5 units. So again, here's the output, and then I'm going to increase the output by 5 every single time. And the new expression that would represent that would be the negative 5x, and then I guess it would be plus the number 8. And I could give both of these expressions different names, and I can write them down. For example, I could say that this is now the function g of x, right? And g of x is the function that you get when you take the function f of x and you increase its outputs by 5 units. So I could summarize that up as, oh, this new function I built, g of x, is equal to negative 5x and then plus the number 8. So again, what you see here is I have both the description of what's happening and the expression that replaces that. And this is just bonus material, right? This is nice bonus material, but let's move on past that. All right, let's look at the final question here on Part A, this 2-page part of the study team test. It says solve each system by using the method of elimination. Uh-oh. Oh, we're specifying elimination here. Okay. Well, if I want to use elimination, let's see. There's options, of course. I think just because the numbers are slightly smaller, I think I'm going to choose to multiply this top equation through I'm going to go with negative 5 up here. So I'm going to put parentheses around the entire top equation. I'm going to multiply all the terms on both sides of that by negative 5. And for the other equation, I'm going to multiply both sides by a positive 3. Now, that's what I'm going to do, but let's talk about the y and how I'm selecting that. I've decided that I want my y values to eliminate. And I can see that as I have it right now, I've got the y values of negative 3y and negative 5y. Well, I know that if I'm going to use elimination, especially with the subtraction version of it, which is what we most often do, I want those to be opposite in signs. I want them to, one be positive and one negative. So that's why I chose the negative 5. And in the top one, it's going to make that y coefficient the number positive 15. And by choosing 3, I'm going to make it a negative 15 down below. So that'll help those y values eliminate. Now, what I like to do when I'm doing this is very carefully rewrite the equation so that I have a chance to visually check for errors. So again, all terms on both sides. So the first term on the left-hand side is a negative 5x, and when I multiply that by the 5x, I'm going to get exactly 25x, and then I'm going to multiply negative 3y times negative 5. I'm going to get a positive 15y. And then finally, I need to multiply negative 5 times a negative 23, and that's going to give me positive 115. Okay, so I'm going to do the same thing now, except now with a negative 3 for the bottom equation. Every single term on both the left and right hand side is going to be, it's going to pick up a new factor of 3. I'm multiplying through by 3. On the left hand side, this is going to become 21x, and then it's going to become a 3 times negative 5 would be a negative 15y. Not an accident that that happened. That's exactly what we're going for. And then finally, 3 times negative 23 is going to give me negative, yeah, it will be negative, because only one of those is negative, negative 69. Finally, we're going to go ahead and combine here. Well, finally, that makes it sound like we're done. We're just going to combine these. I have equal things. I'm adding equal things, so it will result in a collection of equal things. Of course, my 15y and my negative 15y are gone, and I'm going to be left with 46 times x. And when I combine the two things on the right-hand side, 115 and negative 69, I get a positive 46 also. This is like the best possible equation to solve. I can do it. I get that x is equal to the number 1. Now, of course, that's not a solution to the system. That's just a value of x where the solution happens. The solution is the xy pair that makes, both equations true. I think probably that second equation would be fine. So I'm going to use that. I'm just going to write it was 7 times x minus 5 times y gives me negative 23. My x value here is positive 1, so I've got 7 times this positive 1 minus 5y equals negative 23. I'm going to subtract 7 from both sides. When I do that, I get negative 5y is equal to negative 30. And then finally, I'm going to divide both sides by negative 5. Y equals, see, negative 30 divided by negative 5 is positive the number 6. So there we go. I now have my solution. It's this ordered pair where x is 1 and y is 6. And I could plug those quite nicely back into the original problem. And I do in both cases get that I would get negative 23 on both of those. So yes, that value of x and y produces negative 23 both of the times. Okay, that is it for part A of the study team test. I will post up other videos that include part B, C, and D. This is Mr. Roberts.